So, I know Bohr and Schrodinger blew your mind with all their information. They know so much more than we, as in Dalton and Rutherford and JJ. I mean, thank you guys for getting us started, but now we really got to delve into the details of the modern atomic model, aka Bohr's model, and then the quantum mechanical model, which just sounds crazy hard, right? But we're going to kind of skim the surface on a lot of this stuff. Bohr's model, we're really interested in how it relates to light. That's basically what Bohr's model is, why it's so important to us. And we're actually going to see excited electrons. We're going to see them emit light. We're going to electrocute some electrons. We're going to heat up some electrons, and we're going to see how they react to that. So I want to talk about Bohr's a lot first, but before we actually talk about Bohr's, we're going to talk about light. Light is cool. Light is part of the electromagnetic spectrum, but the electromagnetic spectrum is just a bunch of waves. That's it. You would think they were all the same, but they're not. Waves come in many varieties. They come in really long waves and slow, or they come in really, really fast waves and really energetic and high frequency, high energy. So then there's a large spectrum in between, aka the electromagnetic spectrum. It's a lot of stuff. So with the waves, we have to talk about two key features. Anytime I have a star, it means it's on the paper someplace. Just kind of fill it out. Not everything I have today is on your paper, but I tried to help the brother out so you don't have to write everything. So the wavelength is literally the length between two crests on a wave. But length is measured in what generally? What units? Shout it out. Meters. Generally it's in meters. But we're dealing with itty bitty tiny waves. So a lot of times today you'll see me express length in nanometers, and you'll have to convert back to meters in order to utilize an equation, the speed of light equation we're using today. I got you, Jack. All right, so amplitude is the least important variable up here. Frequency and wavelength are the more important ones. Wavelength is denoted by this ugly looking upside down Y called lambda. Lambda is a Greek, I can't remember what letter that is. And it's denoted, or it is supposed to be in units of length, aka meters or nanometers. Frequency is going to be in units of per second. So one over second meaning per second. Seconds to -1, which means the same thing as per second. Or hertz. You know people like to name stuff after them, right? Guess who helped with this?
Hertz.
Hertz, Mr. Hertz, Dr. Hertz. Eventually you guys will see in your lifetime millennium, it will happen. I'm going to get on that periodic table. I'll be 120 or whatever up there. So it'll happen. And you'll be like, that was my chemistry teacher. Okay, so frequency is noted as a V. It's related to velocity, but a lot of our guys you probably saw were not only chemists but also physicists. So that kind of shows the connection between all the physical sciences. So we're going to use this V as, it's like a V with a little tail inside, kind of like that micro, but it's definitely related to physics more than chemistry. So we're talking about just number of cycles per time, per second in our case. So how do these things come together? Amplitude, just know that it helps with intensity of light. So if you have a really, really bright, intense substance, its wavelength, or it's amplitude here, I drew like a dashed line between here, its amplitude would have a really high height. But if I have a low intensity light, its wave function is going to be more shallow. It's like a sine and cosine. Do we know what I'm talking about? Okay. It's shallower right there, so it's less intense, and it's just the brightness of the light. We don't deal with amplitude that much. Okay, but the relationship that we do need to know is how these both relate to the speed of light, c. And the speed of light is a constant. Every electromagnetic spectrum wave, anything in the EMS, should travel at the speed of light. Any energy wave will travel at 3.0 times 10 to the 8th meters per second. Really, really fast. But that means that you can create a direct or indirect relationship between the two things that are the product that equal to the speed of light. So let me show that equation. The equation is C is equal to lambda times frequency. What does lambda stand for? Wavelength. What is wavelength supposed to be measured in? What units? Meters. Okay. What is frequency measured in? Per seconds. Thank you. Per second. So it's over seconds. 1 over seconds if you'd like. And so when these meters in the numerator and seconds in the denominator, when they come together, they make meters per second, right? That's why, because they are constant, or they are equal to the constant, the speed of light constant, which is measured in meters per second. So if and this is just a algebra kind of relationship here. If I increase one variable, let's say I increase the frequency, what's going to happen to the wavelength if this is a constant? It's going to decrease, right? So as one goes up, one goes down. Direct or indirect relationship? Direct. Okay. So that means you can have really long wavelengths, but their frequency is really slow. Or you can have, so these are long, right, from here to here, the wavelength is large. Or you can have little wavelengths that move very, very quickly. And moving quickly means moving fast, right? So increasing velocity or speed. But their wavelength's only like yay big. So the relationship is indirect. Cool with that? Okay, let's do an example. All right, so, and this is everything I've talked about. We're not going to talk about every little detail of each of these. We're really focusing on visible light, which is this little bitty section of the electromagnetic spectrum. We can only see very little energy. We can hear radio waves, which are really, really long, like, half as long as this room. Radio waves that hit your radio and make noise, and you can hear them. We can feel, well, we can't feel it. We can feel infrared, which feels hot. We can see X-rays in a way after they've kind of been manipulated. We can definitely feel the after effects of UV. Gamma, has anybody ever experienced gamma? Nobody's a Hulk out like on the side, right? Okay, that would be pretty awesome. So anyway, you can see gamma are really tiny, 10 to the negative 14th, that's crazy small. And then radio waves are very large, 10 to the 4th meters, very large. And we're kind of dealing with stuff in the middle. How are you going to remember violet on the ultraviolet side? Ultraviolet on the other side of violet, right? How do you remember red is near infrared? Oh man. I know. You gotta work with me here. You really can't forget that red is near infrared and violet is near ultraviolet. Just remember that kind of general rule of thumb. They sound very similar. Okay. So let's do this first example. This one's not on your paper, so write it down if you need to. I guarantee you'll need to. Okay. So frequency of light, what is the frequency of violet light at 400 nanometers? Same way I've always done a word problem, okay? I do a word problem by first identifying my unknown. Question is frequency. We need to practice by determining what we're looking for and the units we're looking for, okay? So for this one, for frequency, what units am I looking for? Something per second, right? So I'm not looking for meters per second, I'm just looking for something per second, so we just call that per second. So I'm looking for seconds to the -1, or per second, or hertz if you given to the problem, but that's not given to us in this problem. So we're looking for something with time. Okay, and we're given, a given of ours is 400 nanometers. What else is a given that will help us relate these two, but it's not literally written out in the problem? Right, the speed of light. C is equal to 3.00 times 10 to the 8 meters per second, which is equal to lambda times frequency. All right, so what do you notice that this looks funny to me? What should I do with that first? Convert to meters, because I can't use nanometers in a problem with meters, because I can't cancel units, and then I'm in big trouble. Okay, so I need to 400 nanometers times what unit do I want? Meters, and I want that on top. So what unit do I want to get rid of? Nanometers. So you see the dimensional analysis. If you didn't study enough Unit 1, it's going to come back and bite you in the butt a little bit, because you'll probably be able to do this part really easy as algebra, but you got to get through dimensional analysis first. Okay, so how many nanometers are in a meter? In your head, you're going what? 10 to the 9th, right? So you said King Henry died by drinking chocolate milk, ... micro, ... nano, ... pico. And I didn't tell you guys this last unit because I didn't need to. On the front side of kilo is mega. Mega is 10 to the 6th, where kilo is 10 to the 3rd. Yeah, got me? Okay, that's going to come up in one of our problems. Okay, so anyway, yes, it is 10 to the 9th, because base is meter, 9 zeros over would be nano. So some of us are trying to write some negative exponents. I find that to be harder than writing the positive terms of the exponent. So always assign 1 to your larger unit from the metric system and your larger number to the smaller unit, because there's lots and lots of little nanometers and one big huge meter. Okay, so that's going to give us 4 times 10 to the -7 meters. All right, so I like those units better because they relate to my speed of light. How do I want to solve for frequency? If the equation is c is equal to lambda frequency. How do I want to solve for frequency, people? Divide by what? Thank you. Okay. I really like your participation. Okay, so divide by wavelength to get rid of the lambda from the frequency side, just basically isolating frequency by itself. So frequency is equal to c over lambda. Do I know c? Yes, 3.00 times 10 to the 8 meters per second. Do I know lambda? Yeah, I know wavelength, right? I just got that. 4 times 10 to the -7 meters. What unit cancels? Meters and meters. Now, I know it looks funky, and I know most of the time I said do not write fractional units as a plain old numerator or a plain old denominator, but this way it's easier to leave as is. Because what it says now is, oh, I used to know this number. I have to look now. Something to the 14th power. 7.5 times 10 to the 14th. And then the only unit I see is per second. That slash second is per second, which is the unit of frequency, because we just decided that previously up here in the problem. Yay! I would need to round that to 1 sig fig, so 8 times 10 to the 14th per second. That's a frequency. That's super, super duper fast, right? Violet light. Is violet light moving the fastest of the colors, or is red light moving the fastest of the colors? Violet, because it's closest to gamma, which is the smallest wavelength. And small wavelengths move really, really, really fast. Whereas long wavelengths, red's going to be really slow. Not really slow, but slower than violet. Thumbs up if I'm good here. Moving on. Okay, let's do another type of problem. Before we got to talk about light and then Bohr and then light again. So Bohr is the one whose model this light kind of really pertains to, because what he said, and I'm going to come right back up to these notes. You guys already wrote these down on the day we did the notes as scientists. Do you remember this? Any of this at all? Maybe don't, maybe do. Okay. You saw this model, and hopefully my Bohr people are going, yeah, I know everything about that now. What are these rings called, Bohr? What are they called? Orbits, okay. So they're called orbits. Schrodinger, what did you call those things where electrons live? Orbitals or electron clouds, right? So Bohr kind of said these are orbits and these have set paths where the electrons exist. They're certain distances away from the nucleus. And then Schrodinger and Heisenberg and Planck, a bunch of other people, kind of expanded upon that and said, yeah, I mean, they're not exactly there. We're going to call ours orbitals, so a little bit different, or electron clouds. Okay, so these orbitals have numbers. N equals 1 is the first orbital. N equals 2, 2 is right here, is the second orbital. N equals 3 is the third orbital, and so forth. What happens is electrons live in these orbitals. Electrons can move across different orbitals. So they can move from right here in N equals 3, and they can move down to N equals 2. So what you should see is kind of a step system. N equals 1 is the lowest energy, all the way up to N equals infinity, whatever number you want to assign there, to be the highest energy. Okay? Highest energy means really unstable. Those electrons are not happy. They're crazy. They're hyped up on caffeine and sugar. They're not stable. Okay? You guys are chill. You guys are nice and stable, sitting in your seats. You're at the lowest energy level. That's also called the ground state. Ground state. When you're in the upper energy levels, whenever you are excited, guess what? You are said to be in the excited state. So they weren't too fancy with like naming things. They're just trying to really display via words what exactly they're talking about. If you're closest to the nucleus, you're nice and stable, you're grounded, you're low energy. But when the electrons jump up to an outside energy level, let's say energy level, what is this, 5? N equals 5. That means that electron is very, very unstable, and it's going to be excited for a very short period of time, and then it's going to fall back down and plummet. It's like a sugar crash, okay? Falls back down to the ground state and chills at ground state, low energy. Now, whenever the electron drops from an outside energy level all the way back down, there's a big difference in energy. So what did I just say was what related to your high energy or low energy? High, and then here? Low. So there's a big gap of energy, right? Well, what's going to happen to the energy? It's going to be released. If that energy is in the small spectrum of light, we can see that energy. That is the only time we can see energy. If the energy that's associated with that drop is really a high amount of energy or really, really low amount of energy, it's going to be seen as X-ray or IR or gamma. I mean, we can't see that, but other tools that we have in the labs can. So we can only see the ones that specifically are in the visible light spectrum, which you can see in this case, if it's a small jump or small drop in energy, small energy, slow, is going to be the red color. But then we have kind of out here, these outer energy levels dropping to the very inside. That's a lot of energy. Higher energy was the violet one that we talked about earlier. So that's why Bohr's model is very related to light, because sometimes we can see it. So that's what all this information kind of says up here, but I got some more vocabulary, okay? So we just kind of said energy low and then high, but each individual orbit, also called energy level, orbits and energy levels are the same thing. They're just levels of energy. They have a specific amount of energy assigned to them. We like to call that quantized. I don't know why we have to call it that, but that's what we have to call it, quantized. So that each energy level is quantized. But, and we kind of just talked about this too, as the electrons move around their energy levels, they can put off different amounts of energy, which we can see as light. Light is going to be called, or the waves of light that are put off are called spectral lines. And spectral lines are seen from something called a spectroscope. We have spectroscopes. Spectroscope is pretty much a prism. Pink Floyd t-shirt, prism, rainbow, yeah? White light goes in, rainbow comes out. That's essentially what a spectroscope is. So we can look up these lights ahead of us that look white. They're not. They have different colors of wavelengths that are all embedded together. So we can actually see that. We're going to see that tomorrow or Wednesday in our spectroscope lab. So I'm pretty excited about that. Okay, so let's talk a bit more about this. This part is on your paper, kind of the fill in the blank wise, okay? We're going to excite some electrons via electrocution. This one's going to get the electric chair. I'll pull it up here in a second. The highlighted stuff is what you should be writing down. You can draw me some pictures, draw what you want, but I'm going to keep talking. Okay, so I have gases, and this is kind of what Planck did. Mr. Planck, he's on the next slide. He heated up gases via electrocution, or he did like fire. And oh my gosh, this word. Okay, and he could see the different energy put off, right? Well, I'm going to show you this one being electrocuted. This is iodine gas, and to you right now, it's going to look like a single color. Sorry, this breaker. Not sure here. There we go. So this is iodine gas. Right now it looks kind of purpley white. When you take a spectroscope to it, you'll see lots of different colors of lines that are being given off, okay? So it's like a fingerprint. Every single element has its own fingerprint of spectral lines, which are just colorful lines. And they look kind of like this. If I put a spectroscope up to it, I would see bright different colored lines on a black background. It's also called the bright line spectrum because they're bright lines. They were really creative, like I said. But we can see this if we have a spectroscope, which we will have. So, the only reason that's happening is because I'm electrocuting them, so I'm exciting the electrons, are jumping up to unstable state, and they fall back down because they only can stay at the sugar high for a small amount of time. So I'll put another one in a second. This is really hot. So this stays hot because it's like, it doesn't tell me high voltage one, that's all I know. So I'll let that cool down for a minute. I'll show you another one. Okay, so you can see the electrons jumping. So the lights they're getting energized. They come out to the excited state, and then they have to do something with that energy. They will fall back down to ground state. As they fall back down to ground state, they release the energy. And if it's in that just the right spectrum, just the right energy, we can see it as light. So can be seen as light. And if it's really energetic light, then it's purple. And if it's really lazy light, low energy light, it's red. Okay. And you guys can come back if you want to ever draw these drawings. They're there for you on my notes, and I'm videoing too. So I have 19 YouTube subscribers. Where are you people at? Okay. So the bright line spectrum is what Bohr and Planck kind of came together about and said every single element has its own special fingerprint. So this one is not, I don't know which element this is specifically, but I do know that you'll never see an element like this. This is the sun. If you take a rainbow, if you take just a prism, hold it up, and you can split the sun's rays into multiple wavelengths, you'd see a continuum, because the sun emits every single wavelength that it possibly can, because every single organism on Earth utilizes different wavelengths. So we use specific wavelengths to make vitamin D in our cells. Chloroplasts use mainly blue and reddish wavelengths. They have different, very specific ones that they use to do photosynthesis. Whereas bioluminescence or phytoplankton or things like that in the water, they use maybe more of a green or of a aqua colored wavelength to make their energy. So the sun provides everything, every form of energy required so that organisms on Earth can use it, right? Well, different elements are only going to be putting off specific energies of light or wavelengths of light because they only have specific orbits in which they can move their electrons to. And different hydrogen's only got one electron, but it can make 4 different colors of lines from its moving of the electrons up and down those orbits. So think of like potassium or magnesium or anything else with more than one electron, they're going to have like 20 lines here. Okay, so they become these bright spectrums become different as you change up the elements. So this one you'll see when we get to hydrogen in the lab tomorrow. Okay, called bright line spectrum. Okay, moving on. Thank you. All right, so don't write down this up here. We've already seen this happen. I just showed you here. You've already seen this happen before in real life. Okay, neon lights, different colors. That's just a bunch of different elements that are exciting with electricity. So, the only word that I need you kind of to associate with this is that we are literally seeing photons. Photons, we used to say they're massless. Because does energy have mass? Is energy matter? Yay or nay? No. Nay. Okay. We previously said in Unit 1, no, energy is not matter. It doesn't have mass. It doesn't have volume. It doesn't act like that. You can't put it on a scale and weigh energy. Like you can't weigh X-rays. You can't weigh light. But as we start to get to more of the quantum mechanical model and the modern theory stuff, we start to bend our rules some because not everything's going to fit that nice cookie cutter theory. So that's why I need to talk about photons first. So we commonly just say photons are a quantum of light or a bundle of light. Okay, and that's going to come into play on our next slide in a second. We're going to talk about the photoelectric effect. I will show that little simulation there in a little bit. So let's talk about photons a bit more. We'll have to tell you about Planck first. Okay, so now we're talking about Planck because eventually we got to get to Schrödinger. So Bohr was great. He decided that, or him and the scientific community said, good job for hydrogen, man. Applaud you. This doesn't work for anything else, though. So we need to get some more knowledge. We need to get some more information. So Mr. Planck said that, okay, well, let's start studying some different materials and see if we can get the energy associated with it to see if there really are these things called orbits that Bohr proposed. So he studied these hot glowing solids, and he actually was one of the first people to say this light coming off that has energy, it also has a frequency. So we already knew they had a wavelength, but frequency was kind of lesser known. Sorry, I'll pull this down. And then Einstein comes in the picture. So let me tell you about this first. So we're going to talk about velocity in terms of chemistry. It's kind of more physics, but we're going to relate these two and say they are one here. So he said there's an energy relation to the velocity and the wavelengths we've been talking about so far. And he came up with this relationship. E is equal to hv. E is energy. H is Planck's constant. 6.626 times 10 to the negative 34th joule seconds. Why does joule have to come into play here? What are we talking about? Energy. So that's why we have to have that unit present. And then he said it's related back to the frequency, right? So this makes sense. Energy is equal to, energy, which is measured in joules, is equal to Planck's constant, which is blah, 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 joule seconds, and times frequency, which is what unit? Frequency. Hertz or per second. I'm just going to write it per second so you can see the cancellation. Okay, so there we go. Seconds cancel with per seconds, leaving with joules, which is an energy unit. So it does work. So we now thank Planck for this because now we actually can calculate the energy at any energy level and any form of light or energy, not just light. Einstein kind of said, okay, yeah, good job, Planck. Very, very good. But now this photon stuff you're talking about, it's got some energy, it's got a specific wavelength, it's got a specific frequency. Does it have mass? And everybody was like, no, you're crazy. It doesn't have mass, it's energy. It doesn't have any mass. What are you talking about? Well, Einstein went ahead and proposed, he was working at a patent office, and he had a little time to study physics, and he was like, I think I'd come up with something. He proposed the theory of relativity, which allowed for us to talk about all kinds of things, but I'm going to focus on E is equal to mc squared. What do you think M stands for? Mass. So mass times the speed of light squared is equal to energy that's associated with that mass. Most of the time we don't associate energy with mass. Most of the time we associate mass with mass and energy with energy. But now we're starting to see that they kind of start to come together when it's on really, really tiny nanoscale size. So we kind of bring Planck's energy equation together with Einstein's, and we can come up with this new theory called particle-wave duality. Which means duality, think Jekyll and Hyde, two personalities, okay? All matter in the world has both a particle property to it, meaning it's a particle. It can be massed, it can be held, it can be weight. It has mass and volume to it. Particle means like a matter. And a wave property to it. Wave meaning, what are the two variables we've been talking about this whole day? Thank you, wavelength and frequency associated with it. So that's the wave part to it. So even a bowling ball, even though, yes, it's very much a particle, very, very much is made of matter, it's going to have mass and volume. You can actually measure the wavelength associated with that bowling ball, but its wavelength is going to be so tiny. It's going to be just essentially zero, but we can still say it has a wavelength because it still vibrates at a very, 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 very low frequency. But then we also can talk about single atoms. Atoms have a wavelength associated with them. So that gets into more complex stuff, which I'm not qualified to teach. But we'll talk about it, and I will show that video momentarily. Okay, so now we're kind of starting to pull together the two equations, the speed of light formula and then the energy relation, because now we know they have the properties of both, so we can start to relate them together. So let's do this problem. This problem is on your paper. And I'm also going to ask this question, what is the frequency of light and the energy associated with it, because I didn't put it in. So I give you the two equations above. You know which ones have constants in it. Let's go ahead and try this. The helium neon laser emits light at a wavelength, so we know the wavelength, of 633 nanometers. What is the frequency? So what equation comes to mind if you want to go straight from wavelength frequency? Yeah. Okay, so C is equal to lambda times V. I want to solve for which variable here? V. So what am I doing? Dividing by lambda. I always set up my equation before I start plugging in numbers because it's really easy to put the wrong number in the wrong place if you don't, or divide weird. So I always try to do this first. You don't have to, but it's just a technique. All right, so divide by lambda to get V is equal to C over lambda. All right, do you know C? Yes. 3.00 times 10 to the 8th meters per second. Do you know lambda? Kind of. What do you want me to do? You gotta change it to meters because you see, you wrote meters and you go and you're gonna write nanometers, you won't be able to cancel those, right? So what was the conversion again? 10 to the 9th nanos, 9 nanos, it's not too bad. 6.33 times 10 to the negative 7th meters is our wavelength. So 6.33 times 10 to the negative 7th meters. So what cancels? Meters and meters, leaving us with something per second. It's like 4.74, nope, hold on. Yes, 4.74 times 10 to the 14th per second. That is our V, that's our frequency. Okay, so if I want you to now expand this question and find me the energy, what would you do? Energy. What comes to mind? Take the Planck's one, right? So what's the formula?
It's energy equals is constant times the.
Okay, so energy is what we're looking for. Planck's constant, 6.626 times 10 to the negative 34th joule seconds times, give myself a little space here, times the frequency we just achieved, 4.74 times 10 to the 14th per second. I'm actually going to write this in true fraction, so those of you who still are helping yourselves with that, you can see this joule seconds here and the seconds here will cancel, so seconds and seconds cancel. And I think, I don't have that one written down, so I just made that one up. Some number of joules. 3 times 10 to the negative 29, something like that. I don't know what the front number is. Please tell me what you get when you get it. Because like that's 20, that's about 30, maybe a little less, and then the decimal moves over one. So while you guys are waiting, go ahead and try the next one. What'd you get?
3.14.
3 to the 29th? You put a negative there and a positive there. Double check that. 3.14 times 10, hopefully to the negative 29. And don't forget, if you are on the next problem that you have in front of you, hertz is replaceable with per second. They are the same thing. Question? UV has a gas in it. I have to look at it because different gases can emit X-ray and UV and other things. I don't know what gas it is in the inside there. Geokeys.
3.14 to the negative 19. 10 to the negative 19.
Oh, yeah, that is 19. I'm thinking 40, 34. There we go. Negative 19. There we go. Thank you. So it is it seems as if it's a little bit of energy, but we're talking about one photon here, so that's pretty reasonable. All right, do you guys think you could do that? What equation should you be using? First one or second one we learned? The first one, C is equal to wavelength times frequency. We're solving for wavelength, so you're dividing by frequency on both sides. So wavelength is equal to C over V. C being 3.00 times 10 to the 8th meters per second. V being the frequency given as is, you can change that hertz to per second though, so 4.80 times 10 to the 17th per second. So it's kind of difficult to see this, but we have per seconds in the numerator and per seconds in the denominator, so both of those cancel, leaving us only with meters, which is the wavelength unit. So we set up good, we just have to calculate. And I do have that. And just trust me on this, parentheses will be your friend, because you will have a hard time, your calculator has a hard time distinguishing by what the heck you're dividing and multiplying here when you have this whole scientific notation in top and bottom. So just put parentheses around numerator and denominator if you're calculating, because it'll save your answer here. You'll get the correct answer versus some crazy large or small number. 6.25 times 10 to the negative 10th meters. All right, so not too hard. We have two equations. Make sure you use the right units with the right one. Any questions here? Nay? Any questions at all? You don't have to whisper them. Okay. All right, so we got the relationship. Oh, we talked about the first relationship. We did the C and D, or we did wavelength and lambda. Tell me, how does energy come into play? If I increase the frequency, what happens to energy? it increases, right? So if I increase the frequency, therefore, since this is a constant, anything that's increasing becomes a constant should also increase what it's equal to. So if these two are directly related, and you told me previously these were indirectly related, how is energy related to wavelength? Directly or indirectly? You got a 50-50 here. Indirectly, because frequency is indirectly related to wavelength, and frequency is directly related to energy. Then, since these two things are equivalent, essentially, then energy is going to be indirectly related to wavelength. So if I had you act it out, you would say, okay, a really long wavelength, so a large lambda, would have a really low energy, so really slow. So low energy because it's so slow, but it's really long wavelength. So yeah, they're indirectly related. All right, cool. So we can do our relationships there. I think I'm going to stop here because this is quantum. I'll show you the quantum stuff tomorrow, but I will show you a video. Okay, so chillax for a minute. Video. Let's do, I have like 5 videos here. We already did photons. Okay, we'll do Schrodinger first. All right, Schrodinger, and this is called Schrodinger's cat, which you've probably heard a little bit about in your presentations. This is a thought experiment that was set up by Schrodinger in an effort to show that when you look at a small subatomic particle, it influences its actions and behavior, which sounds weird, but we're going to see.
Be a YouTube channel without a cat video. So without further ado, we present Schrodinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrodinger preferred pointless gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment.
Called quantum entanglement.
It's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse?
Have we heard of the multiverse theory?
No.
Or what's Olivia Dunham? What movie is that? Hold on. A little bit. No, I have not. He's my. I like me some Jesse Pinkman. Hold on. I'm trying to educate you right now. Hold on. Multiverse. I'm looking for the minute physics ones. 82 minutes? What? No. Minute physics. Yes, okay. We have 2 minutes. Go ahead and pack up, but I'm going to show you this as best as I can.
Everyone loves the idea of parallel universes. The appeal of an ideal world where you have second chances and things turn out differently. An alternate reality where you do get into Hogwarts and the Star Wars prequels aren't made and you finally plug in your asymmetric computer cord correctly on the first try. But is there really a place in science for such wistful speculation? I mean, if the universe is everything that there is, you can't have two versions of it, right? Otherwise, the pair would really be everything, and what you started off calling the universe wasn't. The problem here is terminology. Physicists speaking informally often say universe when they really mean observable universe. That is, the part of the whole universe that we've so far been able to see. And it's perfectly fine to talk about multiple different observable universes. For example, an alien near the edge of our observable universe will see parts of the...
Look for homework online. Start problem set 4. It's not due tomorrow. Test on the desk. Test on the desk.
Oh.
Just leave it on the desk and I will grab it. I have a meeting during lunch today. I have a meeting almost every day this week. So just hold it until I'll take it. Yeah, I have the power. Okay, it's good. Yes, sir.
So, for like the model, do you just want our atom to be between 4 to 8 inches? Or like,
Here,